Welcome to the Preparing Data and Training a Model with SageMaker demo. This video demonstrates how to use Amazon SageMaker to create and deploy a machine learning or ML model that predicts whether an insurance claim is fraudulent. To train a model in SageMaker, you need to create a training job. The training job includes the URLs of Amazon Simple Storage Service or Amazon S3, buckets where you've stored the training data, and the job outputs. The compute resources that SageMaker will use for model training, and the path to the container image on Amazon Elastic Container Registry, also called Amazon ECR, where the training code is stored. This diagram illustrates the training architecture and resources that I will set up to run the deployed model using SageMaker hosting services. The architecture includes S3 buckets to store the training data, test data, and model artifacts, Amazon Elastic Compute Cloud or Amazon EC2 ML compute instances for training and deployed models, a SageMaker hosting endpoint for the deployed model, and container images for both the training and deployed models, which are stored in Amazon ECR. I will create this architecture using the following steps. First, I will use the AWS SDK for Python, known as Boto3, to create the S3 buckets. Next, I will use the Pandas library to stage, clean, and prepare the training and validation datasets. I will split the original dataset into two CSV files that represent the training and test or validation datasets, and then store them to the S3 bucket by using Boto3. Next, I will obtain the Docker image for the linear learner algorithm by using Boto3 and the SageMaker API. This algorithm is included with SageMaker, and it's a good fit for this binary classification problem. With the Docker container image ready, I will start the process of training the model by using the training dataset and an EC2 instance specifically designed for ML model training and managed by SageMaker. After the model is trained, I will configure the HTTP endpoint by using SageMaker hosting services and deploy the trained model to it so that production applications can access the deployed model to perform inference. I will then test the model in the deployed endpoint with the validation dataset and assess the precision, recall, and F1 score of the model. Finally, after reviewing the metrics, I will clean up the SageMaker Notebook persistent artifact and delete the deployed endpoint so that I am no longer charged for using it. Okay, let's get started. In this browser, I am logged in to the SageMaker Studio Integrated Development Environment, or IDE. Notice that the notebook is already open, and I've started the Python 3 data science kernel. For this demo, I'm not going to explain how to use the SageMaker Studio IDE. Just know that Jupyter notebooks are processed by each cell from top to bottom. In this demo, I will briefly explain what each cell does, run the cell by pressing Shift-Enter, and then review the output. First, I will use Boto3 to create an S3 bucket to store the training and validation data and capture the model artifacts. To create the bucket, I will choose the first cell and press Shift and Enter keys together to run it. The result displays the S3 bucket location for the data and artifacts. To confirm the bucket was created, I will open the Amazon S3 console, and I can see the bucket listed here. Now, I will use the pandas Python library to stage, clean, and prepare the data. Notice that I am loading the insuranceclaims.csv file into a data frame. Then I will delete some of the unnecessary columns and convert some of the values in the columns. This is part of the feature engineering phase. Next, I will randomly select records from the original dataset to build the training and validation datasets. After I run this cell, the training and validation records are stored in memory as separate datasets. A report, as a result of the cell, is generated in the notebook and indicates the number of records for each dataset, along with the features. Now that the training and validation datasets are created and stored in memory, I will use Boto 3 to save them to Amazon S3. To do this, I choose the cell and press Shift-Enter to process it. The result displays as an output after the cell. The output includes the locations where the training and validation datasets are stored. To look at the output, I return to the Amazon S3 console. I choose the name of the bucket. Here, I see that the insurance fraud prediction folder has been created, which corresponds to what you saw in the notebook. I can see the datasets for training and validation data. For now, I only have the data subfolder, which contains the training and validation dataset files. Later, a folder for the model artifacts will be created. Now that the data is stored in S3, cleaned and prepared, it's time to obtain the Docker image for the linear learner algorithm that is built into SageMaker. I will use the SageMaker API to grab the Docker container in the current region, which is US East 1. I am using the AWS Identity and Access Management, or IAM, role named Get Execution Role, so that I can use SageMaker commands. This will be needed later. To make it easier to find my modeling artifacts later, I am going to generate unique names for the artifacts. You can see this at the bottom of the cell. This will generate a unique name that includes the timestamp the artifact was created. This aligns with best practices for traceability. As with previous cells in this notebook, I will run the code by pressing Shift-Enter. The result is that the Docker container image is pulled, and the location is displayed in the cell's output. This next cell is all about configuring the training job. There is a lot of detail here, and most of this detail is for data scientists working with the model. I will briefly demonstrate what is happening in this cell. This cell does 4 key things. First, it configures the training job, including using the default hyperparameters to further configure the model. Hyperparameters are like switches that tune the model for a certain type of model performance. Second, this cell associates the training job with the data in the bucket I created earlier. Next, the cell identifies where the model artifacts will be stored after training is complete. Finally, after the code is processed in this cell, the training job will start and process the training dataset to train the model. The output of this cell is a statement that the training job has started. As a data engineer, I might want to see training jobs and their status. I can quickly review this in the SageMaker console. In the navigation pane, I choose Training and then Training Jobs. As seen here, I can see that my training job is now in progress, and SageMaker is downloading the training image. The next cell is designed to provide the status of the training job while it is running in the background. I will run it again by pressing Shift-Enter. Notice the status is in progress and shows time elapsed. I have mainly added this code to illustrate how a notebook can provide the status of a training job directly. At some point, the status changes to complete. You can confirm this by returning to the SageMaker console and choosing Training and then Training Jobs in the navigation pane. This is helpful because depending on the data you have, training jobs can take many minutes, hours, or even days. Notifications can be built within AWS to notify the team when a job is complete. The next cell in the notebook checks to see if the model training job is complete. If it is, the output includes the Amazon resource name, or ARN, of the model definition. I can also review the details of the model definition in the SageMaker console by choosing Inference and then Models in the navigation pane. All models created within the SageMaker domain are listed here. It's important to create naming conventions to document the model and its purpose. I'll choose the model name, and this takes me to the Model Details page. Notice that the IAM role, ARN, that was used to train the model is listed. The training job that is associated with the model is also listed here, and the model location is provided. This is where the model is stored in Amazon S3. I'll choose the link for the model data location. This takes me to Amazon S3, and I can see that the model.tar.gzip file is listed in the output folder of the bucket. If you want to share the trained model with someone else using AWS, you can do so by sharing this file. The next cell in the notebook configures a SageMaker endpoint for the trained model. Note that this cell only configures the endpoint. It doesn't deploy it. To process the code in this cell, I will press Shift-Enter. The cell's output includes the ARN for the SageMaker endpoint. To see more details about the deployed endpoint in the SageMaker console, choose Inference and then Endpoint Configurations in the navigation pane. With the endpoint configuration now created, it's time to deploy it in production. I will run this cell. The endpoint is deploying. This configuration will take approximately 10 to 12 minutes. I will pause the demo and return when it is complete. Now the endpoint is in service, which means that the model is ready for validation. To validate the deployed model, I first need records from the validation dataset. This cell loads records from the validation dataset into a data frame and then lists the shape of the data. Adding the records to the data frame allows you to quickly use Python code to determine whether each record is fraudulent. The purpose of these next two cells is to print a report of true negatives, false positives, and true positives, and generate counts of these. This information helps you to compare the predictions made from the model against the actual data and generate performance metrics for the model. These cells focus on the data scientist's work, but are included here to show how a model is validated. Now that I have counts of the true negatives, false positives, true positives, and false negatives, I can use these along with formulas to calculate the performance of the model. Key ML metrics include precision, recall, and the F1 score as shown here. These metrics help a data scientist determine if a model is ready for use in a production environment. At this point, the team would review the model's performance against their goals for the overall ML solution. Then, they could either further refine the model by seeking out more data or tweak the performance of the model with further hyperparameter tuning. If they determine it is ready for production traffic, they would point their production application to the endpoint so that it could generate predictions on incoming records. From a data engineer's perspective, the demo is more or less complete, except for an important step. I need to make sure that I clean up resources from this demo so that I don't continue to be charged for active AWS resources. When a model is deployed behind an endpoint using SageMaker's managed deployment environments, unlike local test environments, the result is a persistent artifact, backed by an instance that will run until terminated. You are charged for running instances. Therefore, it's important to delete resources that are no longer needed. You should always delete an active and running model endpoint when the work is complete. To do this, I will use the following methods: SageMaker.deleteEndpoint, SageMaker.deleteEndpointConfig, and SageMaker.deleteModel methods in my code. In summary, you have seen how to create a model in SageMaker to predict whether an insurance claim is fraudulent. You have also learned how to retain the model for long-term usage, while being able to create and remove AWS infrastructure to build, train, and host the model. Thanks for watching this demonstration. Welcome. In this video, I'll show you how to use Amazon SageMaker Canvas to create a machine learning or ML model to predict whether an insurance claim is fraudulent. The diagram shows what I will accomplish in this demonstration. First, I will log into the SageMaker console as a user who doesn't have an administrator role. Note that I already used an administrator user to create a SageMaker domain and grant the AWS Identity and Access Management, also known as IAM, permissions that this user needs to use SageMaker Canvas. Next, I will import an insurance fraud dataset into Canvas from Amazon Simple Storage Service or Amazon S3. Then I'll preview the data in Canvas. I will also select a target column in the dataset for the prediction. SageMaker Canvas will then recommend the types of models that I can use based on the dataset. I will then preview the model to understand how well the model will make predictions without having to do a quick or standard build of the model, which can take hours. I'll now prepare and analyze the data. Steps during this phase include reviewing the model recipe and feature engineering, where I'll make changes to the dataset that determine how the model is trained. Next, I will do a quick build of the model. A quick build is shorter than a standard build, but might not be as accurate. After the quick build is complete, I will evaluate the model using the Scoring tab in Canvas. I will also use the Single Prediction option to test the model's ability to make predictions on new data, and I'll review the results. Finally, I will show you how to retrieve the model artifacts and remove SageMaker Canvas resources. Okay, let's get started. To access SageMaker Canvas, I have logged into the AWS Management Console as a user who has IAM permissions to access Canvas. To access Canvas, I search for SageMaker Canvas in the search bar at the top of the console and then choose the SageMaker Canvas feature. I make sure that I'm in the US East 1 or Northern Virginia region in the console. On the control panel page in the navigation pane, under Control Panel, I choose Canvas. I now see the SageMaker Canvas page. Under the Launch Canvas section, I see the default user that was created when the SageMaker domain was created. To access SageMaker Canvas, I choose Open Canvas. Because this is the first time I've used Canvas, the screen indicates that SageMaker Canvas is creating an application. The application takes a few minutes to load. I'm going to pause the recording and return when this step is complete. Welcome back. After a few minutes of initial setup and configuration, here I am in the SageMaker Canvas app. I notice that the Welcome to Canvas pop-up is displayed. I'm going to close this for now. Because this is my first time using SageMaker, the service created an S3 bucket with the following pattern: SageMaker, my region, my account ID. In the next step, I will upload an insurance fraud dataset to this bucket. First, I'll navigate to the Amazon S3 console in another tab. In the buckets list, I see the bucket that SageMaker Canvas created for me. I choose the bucket name, and then I choose Upload. I choose Add Files, select the dataset file, and choose Open. And then scroll to the bottom of the page and choose Upload. Now SageMaker Canvas will have access to the file before building the model. Now it's time to import the dataset into SageMaker Canvas. I return to the tab with SageMaker Canvas open. To import the dataset, I choose Datasets in the navigation pane and then choose Import. I have two options to upload the file: Upload and S3. Upload allows me to upload any file from my desktop, and S3 allows me to upload a file from an S3 bucket. I choose S3. I choose the bucket name that includes SageMaker, my region, and my account ID. Then I select the insurancefraud.csv file. Two options appear at the bottom of the screen: Preview All and Import Data. I choose Preview All, and the first 100 rows of the dataset are displayed, with all columns in the dataset. I quickly review what will be imported by scanning a few of the records and their columns. I am happy with what I see and ready to proceed, so I choose Import Data. Now that I've imported my data, it's time to begin the model build process, including setting the target variable. The target variable is what I want to predict. I also need to inspect the properties of the data. To begin the model creation process, I choose Models in the navigation pane and then choose New Model. The Create New Model dialog box opens. I will enter the insurance fraud as the model name and choose Create. Within SageMaker Canvas, the new model creation process consists of 4 steps. The Canvas user interface represents these steps as 4 tabs. The first tab is Select. This is where I'll select the dataset to use for the model. Build is the second tab, and it's where I'll configure and initiate the build process. After the model is trained, I'll use the third tab, Analyze, to look at the model output and performance. And on the Predict tab, I can use the trained model to make a prediction against a single new record or against a series of new records, also known as batch or bulk. I'm on the first tab, Select. I'll choose the insurance fraud dataset and then choose Select Dataset. Canvas moves to the build phase. I need to choose the target column. For this dataset, I will use Fraud Reported, so I choose it from the drop-down menu. SageMaker Canvas automatically tries to infer the ML problem type and shows it in the Model Type section. Because I am interested in whether a claim is fraudulent, Canvas recommends 2-category model as the model type. Another term for 2-category model is binary classification. The next step in the build phase is to review the proposed model recipe, meaning the features that are included in the model to make predictions. Here, I can also review dataset statistics, including missing and mismatched values, unique values, and the mean and mode for each column in the dataset. This information helps me with the data exploration and feature engineering phases of the ML process, and I can use these statistics to drop some of the columns if needed. For this particular ML problem and the insurance fraud dataset, I've determined that I need to remove the following columns because they won't help with the ML model. These are policy number, policy bind date, insured zip code, incident location, and incident date. Notice that these have either a negative correlation to the target or no correlation to the target. Because I don't want to use these columns with the model, I can drop columns by clearing their checkboxes. Now I can train the model. SageMaker Canvas offers two methods for training, Quick Build and Standard Build. Quick Build usually takes 2 to 15 minutes, whereas Standard Build usually takes 2 to 4 hours and generally results in higher accuracy. Quick Build trains fewer combinations of models and hyperparameters to prioritize speed. This is especially applicable in cases like this demo, where my goal is to quickly develop a prototype model for my use case. For the purposes of this demo, I choose Quick Build. A pop-up window displays and asks me to validate the data. I have two options: Start Quick Build and Validate Your Data. If I choose Validate Your Data, Canvas will check to see if there are any issues with my dataset to avoid any potential failures while building the model. I choose Validate Your Data because I haven't completed the validation step yet. Notice the blue bar at the top of the page. No issues were found in the dataset. Now I can start the Quick Build again. Again, I choose Quick Build to begin the model training process. I'm now on the Analyze tab in SageMaker Canvas. The Quick Build will take 2 to 15 minutes. I am going to pause the recording and return when it is complete. Welcome back. My Quick Build of the model is complete. I'm going to close this pop-up that asks me how easy it was to build my model. On the Analyze tab, SageMaker Canvas shows the quick training results. This model can correctly predict fraud 83% of the time. Machine learning introduces some stochasticity, uncertainty, in the process of training models, which can lead to different results with different builds. Therefore, even if you have used the same dataset, model type, and features, you might see different performance if you built the model again. On the Overview tab, SageMaker Canvas shows the column impact, or the estimated importance of each input column in predicting the target column. In this example, the incident severity column has the most significant impact on predicting whether a claim is fraudulent. To simplify the information presented here, I am going to filter by Y for fraud reported. On the right panel, you can see the direction of impact of incident severity on prediction of fraud reported. I am going to choose Y over the default value of N so that I can further illustrate what is being represented. For example, with the insurance fraud dataset, when major damage is reported for this field, it has a higher incidence of fraud over the other values, minor damage or total loss. Now that my model is trained, it's time to use it to make predictions. To start making predictions against new data, I choose the Predict tab. The Predict tab has two options. The first is Batch Prediction. With this option, you can make a prediction for each record in a new dataset that is formatted the same way as the original dataset. With Single Prediction, you can experiment with each individual feature and see what would happen if any value changed. This option is great for further refining your model and helps you get a sense of what the prediction would be if you change the value in a particular column. For this demo, I am going to choose Single Prediction.